the process we went through on Wednesday, where we find a dominating set we think is as small as we can get, and then show that if you pick something smaller, we have a problem, is actually the most common way to find the domination number of a graph. So that's the procedure most of the time. If I say, here's a graph, what's its domination number? We'll try and find a dominating set and then see why we can't do it with anything fewer. But some of them are structurally easy to define. Kn is a complete graph on n vertices. Domination number of Kn. Why? So if everything is connected to everything else, then we really only need one vertex, because its neighborhood will be everything else, including it. I'm done. So this one is structurally 1. I don't have an opportunity to try and pick a smaller number of vertices and go from there. I'm kind of stuck at that point. I can do that in 1. Okay, you win. Still 1, because that 1 in the one partite set is connected to everything else. Normally, I draw that 1 in the middle. That's a star. So let's try something that's a little more difficult, not intuitively, immediately obvious in my head. A cycle. Four of n over 2. Tell me why n over 2, and then we'll figure out why 4. That is true. If I take every other vertex, it goes from one to the next. But domination occurs in the whole neighborhood, to both sides. So I don't need every other vertex. Any vertex neighborhood, closed neighborhood, is how many vertices? Closed neighborhood. Itself, the neighborhood is. So I can, instead of doing n over 2, do n over 3. Floor or ceiling? Let's write a couple of cycles. Draw me some cycles. Let's do 3, 4, 5, 6, 7. Remember, I'm using that bar when I think of neighborhoods to mean closed neighborhood. I ran out of room by the time I got across to 6. We'll do 7 afterwards. If I'm looking at C3, how many vertices do I need? Just one. C4, 2. If I used floor then over 3, 4/3 would round down to 1. So maybe floor is not right, maybe ceiling is right. But that would mean for 5, I should need 2 as well, right? Can you do it in 2? Sure. That covers these 2. I just need to cover one of those with the other. But then this one should also be 2. Which 2? Any diametrically opposed pair. I can use the sides, these two, any diametrically opposed pair. But 7 should be 3 if I'm rounding up instead of down. Where do you want to start? Because it's symmetric, I could start at any vertex and try and figure out how to count from there, right? So where do you want to start? So here's vertex number 1, which means I've covered these 2. So I'll go out one more set and not pick those, but I'll pick their next neighbor. So I'll go to my third, wait, 1, skip 1, skip 1, right? I go by 3s. So I go to the next one. And then if I were going this way, now that covers, this is covered, this is covered, this is covered, this is covered. I guess I know what I need to pick for the next one. I should then prove that this works. Ladies and gentlemen, I'm going back to discrete. This is an argument mod 3. The number of these n is 3q plus something, with the something being 0, 1, or 2. If the something is 0, it's going to take exactly n over 3 vertices. If the remainder is 1 or 2, you go to every third, and then you've got 1 or 2 left over. Pick one of those, you've covered those 2 vertices. I did decide I was just going to reason about this one rather than write out a formal proof, because this is example 2 out of the textbook in this section. Okay. But this gives me an idea that I can relate domination number to degree. These are all 2 regular graphs. Every cycle is 2 regular. And so the closed neighborhood had the same size no matter what vertex I picked. then the largest degree or the smallest degree should somehow have something to do with this, right? If I can cover the largest, whatever the largest, what was our symbol for largest degree? Yeah, delta of G. So the closed neighborhood would have size 1 plus that, right? The largest possible closed neighborhood would be 1 more than that. So the fewest number of vertices I could use would somehow have to be related to dividing by that, well, 1 plus that. But wait, there's more. Not only does delta of G give me a lower bound for the domination number, it helps give me an upper bound for the domination number. N minus delta of G. Wait a minute. Why would that upper bound work? This is straightforward enough. I'm going to prove it. Fill in the blank. Each vertex in V of G dominates how many vertices? It's not the same for every vertex, but we do have a number for this. Reese? 3 of V plus 1. So let's pick a vertex with maximal degree. Then I know that that dominates one plus delta of G vertices, which means it misses the rest. The worst of all possible situations is that those remaining vertices are all what? The worst thing for domination. What would be the worst thing for domination for those vertices? Reese? Worse than that. Worse than that. Isolated. They're all alone, which means the only thing they can dominate is themselves. So I would need to choose all of those O and V. And then I would dominate everything, wouldn't I? The dominating set for G includes all of them, O and V. And that means that my domination number is 1 plus n minus 1 minus, okay. There's my upper bound. V and the rest of them. If some of them aren't isolated, then those vertices will dominate more things. I can remove them from the dominating set, and that would make the domination number smaller. But there's my upper limit. How about the lower limit? Well, rather than do this strictly direct, let's do this by picking a minimum dominating set. Each of those vertices dominates 1 plus the degree vertices. Which means the total of all of those things has to cover everything in the graph. So add up I equals 1 to k, 1 plus degree vi. That must be, well, it might not be exact. It might not be a perfect cover, like we had a perfect matching. There might be some left, or things might get covered more than once. But it's got to be at least n, which we said was the size of G. Well, wait a second. One plus the degree of VI is also less than or equal to 1 plus the maximum degree. Right? Oh, that went the wrong way. I said less than or equal to and wrote greater than or equal to. I need to write down what I actually say. Oops. Wait a second. This sentence is true for all vertices VI. So it's true for the sum. But then the thing on the right I'm summing a constant. Chapter 2, Section 4 of the discrete book, Calc 2, or what I hope is a stupid question. I have k copies of the same number. What's the total? K times that number. But K is our domination number. And this total is bigger than or equal to n. Divide to get K all alone. I got the upper limit up there. I got the lower limit down here. These bounds are sharp. They can actually be attained. You can create graphs where the domination number is exactly n divided by 1 plus the highest degree, and you can create graphs where the domination number is exactly n minus the highest degree. Our C6 was such an example. C6 is 2 regular. Was 4n over, ceiling n over 3. N over 3. Questions? I like this one because it sounds like it's impossible to prove, and turns out to be, I just have to count carefully. Page 366. 66? 366. Didn't put my bookmark in the right place. That was dumb. Isn't that pretty? Degrees of the vertices. I cheated. This graph is regular. 3 regular. It's a cubic graph. I don't know what it is, but it's a cubic graph. And they've listed a dominating set, the black colored vertices. 1, 2, 3, 4, 5, 6. Well, that means that the domination number can't be bigger than 6. But it could be as small as number of vertices divided by 1 plus the maximum degree. What's the maximum degree in this graph? So that minimum is actually 5. Well, now I know it's either 6 or 5. So the question is, can you do it in 5? Well, let's consider. There are 3 isomorphic subgraphs here, right? 1, 2, 3. Maximum possible degree is 3, means 1 vertex from each of those would cover 4. Those are subgraphs of size 5, which means if I took off the covers, I now have a graph of size what? 1, 2, 3, 4, 5, 6, 7, 8. I'm only taking out the 4s, right, that I covered with the one choice. So I've got a graph of size 8. Everything's got degree 4. Maybe I can do it in 2. But now I see that I have to cover U1, W1, and V1. Right? The only way to cover W1 is to leave one of these uncovered if I only use stuff from that subgraph, right? So I want to try and get the stuff furthest away from my cut vertices, furthest away from my bridges, and then use something on the other side of the bridge to cover the bridge. But that means I have to cover this bridge and this bridge and this bridge. If I have to cover 3 bridges, I need 3 pieces from that central subgraph. Can I do it in 5? 3 vertices in the middle. The domination number of this graph must actually be 6. Because no matter how I try to cover the outside pieces and the bridges, requires 3 from the outside and 3 from the inside. Questions? Summary of these minutes of discussion. If I have a dominating set for a graph, it means every vertex in the graph is adjacent to at least one vertex in the set. But it might be adjacent to more than one vertex in the set. Which means maybe there are vertices in my set I can pull out. So let's suppose we have some dominating set of, not in, 4, if I have the ability to remove a vertex from my set, then I've found a smaller set. I've gotten to decrease my domination number. Right? At some point, I won't be able to do this anymore. Right? At some point, when you take away a vertex from your dominating set, you miss covering something. Now that really sounds familiar. That sounds familiar. Keep throwing things out until I get a set where no proper subset has the same property. Where else did we use this? I've seen this before. I did a process and I kept seeing, oh, can I actually, is this a valid degree sequence? Yes. And if somewhere along the line, I said, oh, wait, this is not a valid degree sequence, but then the whole thing was thrown out, right? I don't want to throw out the whole thing. I'm just saying, hey, no proper S prime is dominating, but S prime still is dominating. So I didn't throw out the whole baby with the bathwater. I just said, this is as small as I can get. We had a term for that related to coverings, related to edge covers and vertex covers. When we got gamma of G, we found a minimum dominating set, a set of the smallest cardinality. A minimal dominating set is one that you can't make any smaller without losing the property of being a dominating set. We did minimal vertex covers and minimum vertex covers, right? We did minimal edge covers and minimum edge covers. Same exact idea. And it's possible to have a minimal dominating set that is not minimum. Now that sounds absolutely mind-wrenchingly effed up. Here is C8. Two questions. First, this set S prime, V1, V2, V5, V6. Is it a dominating set? Yes. Because V1 dominates V8, V2 dominates V3, 5 dominates 4, 6 dominates 7. So everything is covered. Throw any one away. Which one do you want to throw out? 6? If I throw out 6, then I'm using 1, 2, and 5. Nothing covers V7. V6 gets covered by V5. But neither V8 nor V6 is in this set. I'm missing a vertex. However, C8. What's the domination number of C8? Say again? Not floor, ceiling. Ceiling of 8 on 3, ceiling of 8 on 3 is 3. I should be able to do this in 3. So this is a minimal dominating set, but it's not minimum. Find for me a minimum dominating set. We talked about how to do this. Count mod 3. Pick a place to start. Get through your multiples of 3. Oh, I have 2 now left. Pick one of them. So every minimum dominating set must be minimal. Because if it's a minimum, that's as small as you can get. If I took one away, I'd have a smaller number. That wouldn't work. But a minimal dominating set might not be minimum. Questions? If I have isolated vertices, said it was the worst thing, right? Why? What's the problem with an isolated vertex? So it only dominates itself, nothing else. Its closed neighborhood is itself. So if you've got a graph that's got isolated vertices, every isolated vertex must be part of a dominating set, of any dominating set. So what if I don't have isolated vertices? Right? Then the game gets a little more complicated, right? I got to figure out what's going on. I'm going to say I hope this is easy to understand. If you have a minimal dominating set, then its complement is a dominating set. Somebody tell me why. I'm absolutely sure that this set, VG minus S, definitely hits all of S. Because everything in S is adjacent to something in VG minus S because it's a dominating set. But why is the word minimal in there? Ooh. If I have two vertices that are next to each other, maybe I can take away one. But this set was minimal, and it contained two pair of adjacent vertices. And I couldn't take away one because it was a minimal set, not a minimum. If I have a non-minimal dominating set, then I could include other things from the open neighborhood in the dominating set. Then when I took the complement, ooh, I might have taken out the way to get to that vertex. Here's another upper bound. The last upper bound we had was n minus the maximum degree. But now I'm saying that the dominating number is less than or equal to n over 2. Why the hell is that true? Oh, If I have a minimal dominating set, well, every minimum dominating set is minimal, right? So let's pick the smallest dominating set we can, a minimum one. Well, then V of G minus S should be smaller than S. If it's not, then I have a smaller set that's dominating. Can't do that. But then I have S plus VG minus S. That has to add up to all the vertices, right? And that's bigger than, sorry, less than or equal to number of, that's N. Wait, that's N. N? I got to write this down. I'm starting to confuse myself. Hang on a second. S minimum dominating. Then S is less than or equal to V of G minus S. That's true, because I've counted every vertex either in the set S or its complement. But wait. Replace this by something smaller. Because S is a minimum dominating set, its size is exactly domination number of G. All I had to do was count. Son of a... All right. Here's my curveball for Monday. What if a vertex only dominates neighbors, not itself? How does that change the game? Instead of using closed neighborhoods, I have to use open neighborhoods. I'm up against the clock. We'll talk about that Monday. I will see you all then.